as a magneto-inertial neutron source. Jeff did his PhD at UCSD, and currently he's a postdoc here. Jeff, please take it from here.
All right, thank you for that introduction, Farhat. So like you said, I'm going to be talking to you today about pre-magnetized triple gas puffs as a magneto-inertial neutron source. All right, so the way I've structured this talk, I've split it up into 4 parts. First, I'll give an introduction with some background information on Z-pinches. And then I'll talk about some of the challenges of gas puff Z-pinches for fusion. And then I will hopefully convince you that a couple of those challenges can be addressed by triple nozzle gas puffs. And then I'll conclude the talk with some comments about scaling to higher currents. All right, so for those of you who don't know, a Z-pinch is a cylindrical concept. You have a cylindrical load, you apply a current on the surface of the load. The Biot-Savart law induces an azimuthal magnetic field, and the interaction of those two gives you a J cross B force, which is directed radially inward. There are many different types of Z-pinches. I've only listed a few of them here. The first is wire array Z-pinches. And this is from Rick Spielman's paper where they did some wire array experiments on Sandia. And these are used primarily just to generate large sources of X-rays. Another configuration is the X-pinch. And if you're interested in reading about that, Gail Collins did his thesis work on that. And that's more for producing point sources. So you generate a burst of radiation at the cross point of the X. The third is a gas puff Z-pinch. So this is an image taken from a recent publication by Fabio, actually on the LTD that we have at UCSD that we recently got going. And then fourth is a dense plasma focus. And if you want to read more about that, Krishnan's got a really good overview, a paper where you can read about that. But that's for generating when a deuterium when a deuterium fill is used, that'll generate a beam of deuterons on the axis. So Z-pinches have a long history of neutron and X-ray applications. I won't read the entire chart. I want to thank Farhat for passing this figure on to me. I've got it from Chris Deeney. Z-pinches are among the oldest concepts for fusion. Starting way back in the 50s, they were looking at linear deuterium Z-pinches for fusion. And that's also when plasma focus research started. In the 60s and 70s, with the advent of pulse power and wire arrays and gas puff Z-pinches, you could do all sorts of interesting experiments. The bulk of Z-pinch work is pulse power driven K-shell radiation sources. So I'll be talking a bit about that later. And over the decades, more and more powerful generators were able to be used. And one addition I made to this figure was in the early 2010s, magneto-inertial fusion went through what you might call a renaissance of sorts, with things like maglev coming onto the scene. So briefly, why might you use a gas puff Z-pinch instead of a wire array Z-pinch? There are some advantages versus wire arrays. The load is more axisymmetric because you don't have discrete wires. In terms of shot rate, you can do many more shots in a day, so that's a benefit for experimentalists. And you also have some flexibility over the types of density profiles you can use. So you can have multiple nozzles, you can tailor them. Some disadvantages are the number of species is fairly limited. Most of the gas puff work you'll see is just with noble gases and deuterium. And also while you have more control over the initial density profile, it's not always constant. So you have to be careful with measuring it. And on the right, I have a schematic taken from John Giuliani's overview paper on gas puff Z pinches. So if you want to read about it, that covers basically everything you could possibly want to know about gas puffs is in that paper. So this is a time series of a gas puff implosion. All right. So since we'll be talking about deuterium gas puffs, deuterium infusion, it's worth pointing out there are two origins of fusion in a Z-pinch. You have either beam target, which is driven by instabilities, kinetic effects, and then you have thermonuclear, and that's driven by PDV, shock, heating, compression, etc. For pure deuterium, the literature, generally the opinion of the literature is it's predominantly beam target at low currents and predominantly thermonuclear at high currents. I want to caveat that with I'm not aware, although I could be proven wrong, I'm not aware of anyone who's looked at multi-species Z pinches like the ones I'll be talking about today. But whether it's beam target or thermonuclear, they both theoretically scale as I to the fourth. And you can read Sasha Velikovich's paper to read more about that. On the right is a figure that's going to show up a couple times in the talk. So when we talk about scaling, usually in pulse power, we want to talk about neutron yield scaling with peak current. And so these are various experimental data points that all broadly fall within this range. You can read more about this chart in Giuliani's overview, and Christian might also talk about it. I can't remember off the top of my head. One addition to this, I just want to give a shout out to some of the folks in our group worked with Hafiz Rahman recently, where we did argon and krypton on deuterium implosions on Zebra with a peak current of 1 megaamp and got yields in the order of 10 to the 9. All right, so that's some fundamentals. And now I'll talk about some of the challenges for fusion. So there are, of course, many, and this is more of an overview talk, so this is a simplification. But the two I'm going to talk about today are the Magneto-Rayleigh-Taylor instability and heat losses, and specifically thermal conduction, and I'll explain why when we get there in a couple slides. So if you're not familiar, the Magneto-Rayleigh-Taylor instability is ubiquitous in gas puff Z pinches. The Rayleigh-Taylor instability develops when you have a lighter fluid pushing on a heavier fluid, and when you have Magneto-Rayleigh-Taylor, the lighter fluid is just the vacuum magnetic field. If you want to read a whole lot about this instability, particularly in Z pinches, you could look at Matt Weiss's thesis, or he's also published a couple papers. And other folks of Sandia have done a lot of work on this in the context of maglev. But we're talking about gas puffs, and the purpose of this slide is just to illustrate the ubiquity. So this is the same image I showed a few slides ago from the Giuliani review. You can see MRT, so I'm gonna stop saying Magneto-Rayleigh-Taylor because that's a mouthful. MRT on a 500 kiloamp, 500 nanosecond machine. We also have, these are some Gorgon simulations, I think, of krypton on Z done by Chris Jennings. And I'll be talking a bit more about that paper in a few slides. And then down here we have, these are simulations by Varun Tangri at NRL. They were trying to reproduce some experimental shots on Z. I believe these are with argon. So these are simulations. Yeah, the point I wanted to make is that they show up in simulations experiments. They show up everywhere. And then next we have the zebra. So these are the experiments I was talking about before, where, and this is Fabio's paper showing that MRT develops. And then finally, there's some recent work from at Cobra by Sandra Levine. Incidentally, they actually looked at triple gas puffs with magnetic, with an axial magnetic field, not for neutrons. But that's an interesting paper. So I suggest if you're interested to look at that as well. All right. So now that I mentioned what MRT is, let's talk a bit about how to mitigate it. There are quite a few approaches. I'm only going to touch on 2 of them. They are an axial magnetic field and density tailoring. So in order to explain how that works, I'll just first show you a simplified version of what the growth rate looks like for MRT. So you have the acceleration term, GK. And if you have no magnetic field, then these terms go away and you just have the classical Rayleigh-Taylor. If you have a magnetic field, there's magnetic field line tension that can act to reduce, but it can act to reduce growth, but it has to be in the right direction. So you need an axial magnetic field for Z pinches. And then, of course, there's cylindrical convergence effects, but I'm going to wave my hands and say, for the most part, the things we're looking at, the planar approximation is actually pretty good. All right, so there's this, I'm not presenting anything, any sort of remarkable discovery. We've known for quite some time that a BZ0 can be used to stabilize against C pinches. And so I have a couple examples here. Again, this is Sanders' paper, where they showed that by increasing the axial magnetic field from 0 up to 0.15 Tesla, they saw some significant instability reduction. And then on the bottom, this is from Fabio's paper again. So these are experiments on zebra, where we saw that the pinch is very unstable with 0 Tesla. With 0.15 Tesla, got a little bit more stable, and it was very stable with 0.3 Tesla. Let's see. All right. And the other thing you can do is density tailoring. And so I'm using Chris Jennings' paper as an example of this. There are many ways you can do it. The way he did it in this paper was he started with the base case where there were just two nozzles with this profile structure, and just a snapshot of what that implosion looks like. You see it's incredibly MRT unstable. So one of the things he did was you can tailor you can change both the shape of the nozzle, so you get a more I guess monotonically increasing density profile as you get on the axis. And he put a central jet. And again, this is just a snippet from the paper showing that MRT qualitatively is significantly reduced. All right, so that's a bit about Magneto-Rayleigh-Taylor instability. Now I want to touch briefly on the dominant heat losses. So the first reaction, if I say we don't care about radiation, is probably a bit of skepticism, but because it's very important in ICF. However, it could also be thermal conduction, and in a concept known as magnetized target fusion. And if you want to read more about magnetized target fusion, Irv Lundemeth is sort of the pioneer of that concept. He first wrote a paper way back in 1983, and it sort of birthed the present magneto-inertial fusion, various concepts. But yeah, like I said, the core difference between ICF and MTF is by magnetizing the fuel, and again, I'll touch on what that means in the next slide. But by magnetizing the fuel, you use a much lower density. So you're in a different parameter space, and Bremsstrahlung has a strong density component. So what do I mean by thermal conduction losses can be mitigated by magnetization? So you can go all the way back to, I should have had the reference here, sorry about that. But you can go all the way back to Brzezinski. And basically you have to introduce a concept known as the electron Hall parameter. So that's the omega, it's the electron cyclotron frequency times the electron ion collision time. And if you have a very strong magnetic field, essentially you can sort of cause the electrons to be stuck to the magnetic field lines, if you want to think of it that way. You can write out how strong the Hall parameter has to be. There's this sort of algebraic expression, which I believe is the result of a much more complicated analysis by Epperlein and Haynes. But essentially, the multiplication, the reduction in thermal conduction goes as the inverse of the Hall parameter squared. So if you have a Hall parameter of 10, then your thermal conduction goes down by a factor of 100. Usually you want it to be more than that, but that's just an example. If you've heard of this concept before, in Z pinches, it's probably in the within the context of maglev. So just in case you're not aware, maglev is fairly similar to what I'm talking about today. It's a pulse power cylindrical fusion, Z pinch fusion. You have a cylindrical column of fuel. You heat it with a laser beam to like 100, 200 EV or so, and then you compress it. And the way you mitigate thermal conduction losses is by putting in a fairly large axial magnetic field. And so this is one of the plots from the original maglev paper, just as an example. I think the point design they selected in this paper was 30, and they say if you use a 30 Tesla field, then you get, what is that, a megajoule per centimeter. All right. Okay, so I've talked a bit about the fundamentals of gas pump Z pinches and some of the challenges for fusion, MRT instability and thermal conduction losses. And so now I'm going to talk a bit about triple nozzle gas puffs and why they might be useful for addressing those two challenges. All right, so I've alluded to this before, but triple nozzle gas puffs have been used previously to mitigate MRTI, but usually in the context of X-ray yield. So some examples of this, I think a lot of the original triple nozzle work originated I'm sorry if I say his name wrong, in that group where they did experiments on Cobra. So this is an example. I believe these are MHD simulations. So on the top, they have a double shell, or they also refer to it as an outer jet, inner jet, and then a central jet on axis. Then they compare that with just an outer jet and just an inner jet, and the implosion is qualitatively more stable. This figure in the middle is taken again from Giuliani's review. And all I want to highlight on this is that there are quite a different number of configurations on here. This is in 2015. So the triple nozzle with a double shell in the central jet gave, within the few megaamp range, gave consistently the highest yield. Noting that this is in 2015, I think in 2016 there were some experiments out of Sandia where they looked at triple shell, and the simulations I showed from Varun were attempting to reproduce that, and that's actually what this figure is. And they saw more or less that when you have a double shell with a jet versus a double shell only, sorry, you can't see this axis, but it's K shell power. So the Z2605 is with a double shell. And again, if you want to read more about these experiments, I suggest reading the papers. I put this in here as a joke. The MRTI, there's a concept known as snowplow stabilization, and it'll sort of make sense in the next slide when I show a movie, but I'm not sure how many folks in this audience have actually seen a snowplow before. All right, so what does this look like in simulation? So I'm going to show 4 movies. The first is the sort of base case where we start with just a neon outer liner centered at 2.5 centimeters and on axis. And hopefully this plays. And what I want to show really just qualitatively that the implosion is very MRT unstable, particularly after all of the mass has been swept up by the liner. And so you can stabilize this implosion. You could basically stabilize any implosion just by cranking up the BZ. So let's, okay. So for this particular toy problem, if you throw on a 0.7 Tesla field, then you stabilize the implosion. Alternatively, you can introduce a double nozzle. And for this problem, again, it's not universal, but for this problem, the second nozzle is placed at 1.25 centimeters, and you can see that it's sort of, it sort of helps, but the pinch does eventually break. However, if you throw in a 0.3 Tesla field, you see that the pinch is pretty well stabilized. All right, so why do we care about this at all? So the answer is in the title of this slide. The addition of a third nozzle lowers the required BZ. So for this toy problem, 0.7 to 0.3 Tesla. And that has a remarkable impact on neutron yield, a lot more than you might expect. So for these 0D simulations, and this is also what you get more or less in 1D, you get order 10 to the 9 neutrons. If you stabilize a 0.7 Tesla field, with a 0.7 Tesla field, your yield drops by over 2 orders of magnitude, which is not ideal. However, for the triple liner with a BZ, or sorry, triple nozzle with a BZ, the yield drops by less than a factor of 2, which is pretty significant. All right. So yes, one advantage for using triple nozzle gas pumps with a BZ, it lowers the BZ we need to mitigate MRTI, therefore higher yield. Everybody's happy. The next, so before I talk about the next topic, I'm going to mention, it'll mention looking at different liner materials. So the Z-pinch rule of thumb is if you want a tighter pinch, lower plasma pressure, then increase radiative cooling, all you do is just crank the Z up of the liner. And this image is for any Portlandia fans out there. So I'm going to show results from 9 simulations. What I did was I varied the outer liner was either neon, argon, or krypton, and then the inner liner was neon, argon, or krypton for a 9 total. So keep that in mind. So first, let's look at the outer liner. So the outer liner with neon and then argon and then krypton, there's sort of hypothesis that you just throw in a higher Z, you get more radiation, more compression, tighter pinch, higher yield. That basically holds. So I'll go through this again just to help you visualize. But if we turn to the inner liner, what we find is something similar, but not quite. So with the neon inner liner, that's these three data points. If we go from neon to argon, then, I forgot to mention, sorry, this y-axis is deuterium, it's neutron yield, and then the x-axis is convergence ratio. So convergence ratio is the ratio of the initial radius to the final radius. So the farther you are to the right, the more compression you get. So when we go from a neon inner liner to an argon inner liner, we get more convergence and more yield. However, when we go from the argon inner liner to the krypton inner liner, we get more convergence, but the yield stays the same. So what's going on there? So to explain that, I'm going to introduce the concept. It's very useful for understanding a bird's eye view of how the target is heated during an implosion like this. And it's looking at temperature versus convergence ratio. So it looks kind of funky, but I'll walk through the plot just so to give an intuition. So the first part, when the target's first sort of hit with a sledgehammer, it's shock compressed, you have super adiabatic heating, and I'll explain what that means in a second. But basically, you have a big jump in heating without much compression. You sort of land on this. You land, let's say, a couple hundred EV. And then you go through phase, the target goes through phase of quasi-adiabatic heating. And for a cylindrical implosion, you can just play around with the ideal gas law and get that out. Temperature goes as convergence ratio to the 4/3, and so that's what this black line is. So after the super adiabatic heating, then there's a sort of quasi-adiabatic, it's almost adiabatic, and then there's stagnation. But what I want to point out here is any sort of deviation from constant adiabat means that there's some sort of losses. And so this is the plot for the krypton inner liner, and you can see that there's significant losses occurring. So naturally, the question is, where are they coming from? Well, first we want to ask, do we see those in the neon and the argon inner liners? And that's the yellow and the purple lines here, and they're basically lossless. So that's why with the krypton inner liner, we get more compression without increased yield. It's because the ions are colder. And saying that after the fact is fairly obvious, but at least we can show that here. So then the next question is, why are there more losses with the krypton? And there are two main possibilities. It could be either electron-ion equilibration or ion thermal conduction. And so we can look at this. First, to look at electron-ion equilibration. And you can see from the title, as a spoiler, it's not attributable. But if it were, then the target electrons would have to be much colder for the krypton inner liner than the others, the argon and the neon. So again, this is that same plot, but instead of ion temperature, it's electron temperature. And they're basically the same. The krypton electrons, or the fuel electrons with the krypton inner liner, are on a lower adiabat, so maybe. However, if we look at the equilibration time, this is one formulation of it. It also has to be small, so on the time scale of the implosion, and we can calculate an average value of that in the target over time. And during the implosion, the implosion time scales may be 30 to 50 nanoseconds. That's the amount of time that the liner's actually imploding, or the target's actually imploding. And the equilibration time for this particular problem, it's on the order of 100 to 1,000 nanoseconds. So basically, the ions do not care what the electrons are doing. So this has to be, excuse me, attributable to thermal conduction. So the takeaways from that section, if you use a higher Z outer liner, you get more compression, more yield. If you want to, what appears to be mitigating ion thermal conduction losses, which is possible because we have gas liners that can get very hot instead of a solid liner like a maglev. But you can mitigate ion thermal losses with a neon or an argon inner liner. All right, so there's one more thing I wanted to mention before talking about scaling. If we want to do BZ0 for, oh yes, so yeah, the point I wanted to make is, in addition to stabilizing against MRTI with an axial magnetic field, incidentally, the field you use is large enough to magnetize the electrons. So if you recall a few slides ago, I showed that target electrons are heated without losses. They follow the constant adiabat. And You can do the estimates yourself, but I will argue without giving any numbers. Bremsstrahlung is negligible in this regime. So in order for the implosion to be lossless, the electrons have to be insulated. And we can verify that this is that it's magnetic insulation and not like thermal insulation like the ions, by plotting the electron Hall parameter versus convergence ratio. And you can roughly say that Hall parameter goes as temperature to the 3/2 or convergence ratio squared. And we see that Hall parameter, as you get to higher convergences, regardless of what the inner liner material is, the Hall parameter gets above 1,000, which is fairly significant. And so our hypothesis that the electrons are magnetized, and that's why they're lossless. Everything makes sense. All right, so electrons insulated via BZ. So finally, I want to finish up and talk about scaling to higher currents. So I'm going to recall this picture from before, showing plots of neutron yield versus peak current. So I mentioned before that yield scaling as I to the 4th is true for deuterium pinches, but that it may not be a universal rule. And another question we have is the relevant physics they were talking about. So let me go back a slide. So mitigating ion thermal losses with a neon or argon inner liner, insulating the electrons, mitigating with MRT, or mitigating with a BZ. All of these things may not necessarily hold at higher currents, and that's something I'm looking at right now. Mainly because radiative cooling in the liner goes up. So you end up with a tighter pinch that could affect MRTI growth. And also, like I mentioned, a colder liner. So if the ions don't get as hot, because perhaps the electrons are colder, and so you have more equilibration. But if the ion liner is colder, then we could find out that the ions start to lose. The ion thermal insulation is no longer there. So how do we investigate this? I mean, ideally, what you would do is you'd walk over to Albuquerque and say, let's try this. But of course, that's not feasible. And even something like full-scale 3D MHD simulations or kinetic simulations, which is, of course, what you'd ideally want to do. That's not always feasible. So if you want to scan a large parameter space, you could look at semi-analytic models and then some 1D radiation MHD scans. So I'll be talking a bit about both of those. All right, so semi-analytic models, there have been quite a few papers recently. This is just a sample of them for using to investigate broad parameter spaces. So I'll go through a few of them. The first is, I mentioned before, Irv Lindemuth created, he more or less came up with the idea of magnetized target fusion, or he was one of the early proponents of it. And he did a bunch of parameter scans showing, basically demonstrating that there was this large parameter space between ICF and MCF. And one of the things he did, I just picked a couple figures. It's really fascinating papers if you want to look at them. I would start with the 1983 one, because the others sort of assume you are already familiar with all of the jargon. But as an example, we looked at, he plotted as a function of, I think it was initial fuel, as a function of fuel temperature and ion density, how large a device would need to be to create fusion. So for example, if you had a 1 centimeter long target, I believe he did it both for spherical and cylindrical. I believe this is a plot from cylindrical. If you have a 1 centimeter radius pinch, you need a density I think its initial fuel density, 10 to the 21 to get ignition. And then he plotted RB theta because in that paper he looked at imposing using either a B theta or a BZ to mitigate thermal losses. And so we got an RB theta of megagauss centimeters of about 10 for with an initial ion density of 10 to the 21. And so that's one. Another one that I want to talk about is Ryan McBride came up with a paper. And if you don't know anything about maglev and you want to get a good idea of what all of the basics are, I'd really recommend this. It's very, very approachable. But what he did was he created a semi-analytic model for maglev using MATLAB and explored a bunch of different parameters, things like laser preheating, etc. Just as an example figure, this is similar to the plot that I showed before for maglev, where he looked at for a convergence ratio of 30, what kind of initial BZ do you want? And he more or less reproduced what was in the original maglev paper. One of the interesting things he did more recently was there's some discussion about upgrading Z to a Z300 or a Z800, I think is the other number, with peak currents in the order of something like 45, 47 megaamps for Z300 and upwards of 60 for Z800. And he explored what kind of preheat energy you need, what fuel density do you need, and it's the short answer to how much yield you get is the answer is a lot. So it's again, it's an interesting paper, more of a thought experiment, but still, or at least as of right now, but it's still a very, very interesting paper. And finally, what I want to mention is I created a semi-analytic model. This is very similar to what Ryan McBride did for maglev, but I tweaked it by adding various physics that you have in a gas puff Z-pinch implosion that you don't have in a solid liner. And one of the interesting results, one of the things we were able to get from that is I was able to explicitly quantify all of the various heating and loss terms. And I'd be happy to talk more about this paper later. I don't have enough time to go over it now. But one of the interesting things we saw is intuitively we thought that thermal conduction, so this is electron energy for an implosion. We saw that the main loss term, so this thermal conduction, this magenta here, is the dominant loss term, and radiation doesn't even show up. This is to sort of back up my claims earlier that Bremsstrahlung is not important at this current level, at least, and it very much isn't by many orders of magnitude. And then one of the other interesting things we did with that paper was we looked at how the yield scaled with current, because that's everyone's first question. And these are single liner on target, so similar to what we did at Zebra. And so the model prediction, I went from the point design 850 kiloamps up to, I think, 20. The model predicted something following along this blue curve. These two black lines are the sort of upper and lower bounds of what we see. If you recall the plots I showed of from Giuliani's paper, he actually got it from Burris, I believe. And then there are a couple other scaling laws on here. So there's one right there, I to the 3.5 for Coverdale, and Daniel Clear did something for deuterium as well. And the point I wanted to make was that it's all well and good to have a model, but if it doesn't match up with if you're getting crazy numbers, or you're far off, then there's no use for the model. But we found that the results we got were largely in reasonable agreement, and you can bicker about what reasonable agreement is. I'm happy anything within an order of magnitude in terms of neutron yield. I'm ecstatic. And so to compare it just as a sanity check, we also did some Hydra simulations at various current levels. So we did 1 megaamp all the way up to 20. And there's a bit of difference at the 1 megaamp level, which could be for quite a few different reasons. But as you get into the higher currents, the agreement was actually pretty good. So that was nice to see. All right, so I think I've got about 5 minutes left. So the proposed configuration from the last section for the triple nozzle, if you recall, was to use a high Z on a low Z on a deuterium configuration. And so I did a few quick simulations again in Hydra, just to see how the concept performs. And I want to preempt a question and say, well, how did you scale it? So I scaled, I had the nominal parameters for the UCSD LTD, which is about 850 kiloamps and 160 nanoseconds. And you can just multiply the charging voltage linearly to get a higher current. And if you multiply density by that factor squared, and you multiply the initial BZ, it's just linear. You get roughly the same dynamics. Now it's not exactly the same, but it's fairly close. And we see that at 1 megaamp, we get about 10 to the 9. As you get into the higher, up to 20 megaamps, we agree with more or less we fall in between this upper and lower bounds. They're not getting crazy numbers. But interestingly, once you get to 20 megaamps, so there are two interesting things. Once you hit a certain level of current, it's about, say, between 5 and 10 megaamps. Rather than I to the 4th scaling, you start to get I to the 5th scaling, which is interesting. And I haven't looked too much at this, but generally, what happens is as you get, what I believe is happening is as you get into higher and higher density, the liners are radiating more and more. So that extra boost of yield is from additional compression. So just to throw some numbers on it, at 20 megaamps, we have a convergence ratio of 34, which is on the high side, but it's I think on par with what folks have measured in maglev. The number that comes to mind is they measured stuff on the order of 40, even up to 50. And the point design for maglev is 30. So 34 is a bit of a stretch, but it's not impossible. If you look at average temperature, you get 5.5 keV, and average density is 3 times 10 to the 22. The DD yield is about 3 times 10 to the 14. Just for fun, you can throw on DT, and you generally expect yield to go up by 2 orders of magnitude. It doesn't go quite that much, but 2 times 10 to the 16, you don't get, it's not break even or anything, but it's an interesting yield. I think that's on par with what NIF is currently getting, is on the order of 10 to the 16. All right, so I want to just give a wrap up of the talk, the introduction. Why do we want gas above Z pinches? What are the fundamental concepts? Challenges for fusion are really Taylor instability and thermal conduction losses. And I talked about how triple nozzle gas puffs could potentially address those challenges. You have a lower BZ to mitigate MRTI, and so you get a higher yield. And if you use a higher Z outer liner, you get more compression, more yield. Again, it's a rule of thumb. It's not always true, but it's a good rule of thumb. Possibly we're mitigating ion thermal losses at lower currents with a neon or argon inner liner. And the electrons, at least at the Caesar level, the UCSD LTD level, they're insulated via BZ. And the scaling to higher currents, I'm just doing some quick, again, these are 1D simulations, but krypton, neon, deuterium yield at 20 megaamps could feasibly surpass 10 to the 14, at least in the simulation world where everything is idealized. So with that, I think I'll end. Thank you for your attention, and I'll take any questions.
Thank you, Jeff, for a very informative talk. Are there any questions for Jeff? I see Felipe, you have raised hand. Please go ahead.
Oh, let me allow them to unmute. Okay.
Hi, it's Felipe here. So I'm just curious to know what are the typical mass densities and temperatures that you get in the pinch set for deuterium plasma, for example?
You mean at peak compression?
Yes.
Generally peak compression, I'd have to look to be sure, but the number that pops out is of the order of 10 to the 19 per centimeter per cc. And temperatures, I don't know, I can't remember if you asked for temperatures, but temperatures are on the order of several keV.
Okay, thank you.
There is a question, let me see. I think there's a comment says Paul Schmidt has recently explored scaling paths to magneto-inertial fusion. So there's a reference there.
Yeah, I just want to say thank you, Stephanie. I'm aware of that paper and I forgot to mention it, and I also recommend it. I haven't looked at the Lawson criterion for this particular configuration. I think in order to get any kind of interesting yields, you need to have, I think I did one simulation for, it was Z800, I think. And you get comparable yields to maglev, but at the 20 mega amp level, I think I think yields are probably still far too low. To be actually useful for fusion, you probably need to do this on something like a Z-Next.
Any other questions for Jeff?
Actually, yes. Thanks again, Jeff, for this. These are all almost by definition purely thermonuclear yields, right? There's no beam target interaction. Have you thought about the scaling between the beam target and the thermonuclear? I know there's been a lot of discussion of that over the years.
Yeah, I alluded to this a bit earlier. It's a very fair criticism to say that all of the yield on at the UC on the university scale it's probably predominantly beam target. I'm not aware of any theoretical work. I guess the computational work I've seen is with LSP, but they've looked at pure deuterium when the shift goes from predominantly beam target to thermonuclear. I am certainly interested in looking at this problem with a kinetic code, but I don't have one, so I plug my ears and say it's all thermonuclear. But the generally, what I think would give this concept some more credence is the higher, my understanding is the higher and higher current you go to, the more likely it is to be purely thermonuclear. But of course, I would be thrilled to see this concept explored with a PIC code. I guess it would be Chicago. I'm not aware of any other codes that could do it.
Yeah,
Right.
it's not a trivial problem. Thank you.
So I would like to make a comment. So what I think, Jeff, you were saying that people have looked on dense plasma focus, transition from beam target to pure is not the right word, but thermonuclear. And I think that was scientific work where they showed that if you go above a couple of level, then the contribution due to beam target gets reduced. And predominantly neutrons are due to thermonuclear region.
Yeah, and again, I just want to add, I don't have a good intuition for this, and you'd really have to look at a kinetic code. But my understanding is the beam target yield is predominantly from, it's instability driven, so you get beam, it's on the outer surface of the plasma, and I'd be interested to see how that changes when your outer liner is no longer a fusible material.
Any other questions for Jeff?
I had one actually. So what order of magnitude of current densities do you see on these? Because I know you have here peak current, but I just am wondering like how compressed and like if you have an estimate for how large they get.
I can get back to you on that. That's not a quantity that I usually, that's not a quantity that I often look at.
Okay.
I'm usually just happy with peak current, but I'd be happy to get those numbers for you.
Yeah, I would definitely appreciate that.
Any other question? I have one question. So at 20 megaamp, you did calculations for DT. Have you looked at alpha particle heating?
No. My understanding when I was doing this semi-analytic model, if you recall, I did add an alpha particle heating component into it. If I recall correctly, alpha particle heating at this level is not particularly high. I would have to check that, and it's not really something I've explored much in Hydra because we're not going to get any alpha heating on UCSD.
Okay. Any last chance of any questions you have? If not, let's virtually thank Jeff again.